21 January 1969, Lucens, Vaud, Switzerland. Inside a rock cavern 50 meters below the Swiss countryside, dose rates suddenly climbed to around 1 sievert per hour, in front of an experimental reactor that had been critical for only a few hours. Instrument readings showed a release dominated by short-lived fission products like rubidium-88 and krypton-88, carried by hot carbon dioxide and steam into the confined underground volume. On paper, the Lucens facility was designed so that the surrounding rock would act as a natural containment, limiting any off-site impact and keeping public exposure within regulatory limits. In practice, a single fuel channel's loss of coolant had progressed to fuel overheating, cladding fire, pressure tube failure, and the ejection of roughly 1,100 kilograms of heavy water and molten fuel debris into the cavern. External monitoring posts around Lucens would show only very small doses to the public, well below 0.1 millisieverts. Inside the hill, however, the experimental reactor that was meant to launch a Swiss heavy water line had just suffered the most serious power reactor accident in the country's history, one that would never be restarted. The year 1945 brought Switzerland into a new strategic era. Federal ministries in Bern began examining how the country might develop its own nuclear capabilities without indefinite reliance on foreign fuel cycle technology. By 1955, policy papers described a Swiss reactor line using heavy water and natural or slightly enriched uranium to maintain strategic autonomy. The Studien Commission für Atomenergie, known as SKA, coordinated planning. The Eidgenössische Institut für Reaktorforschung at Wurenlingen operated research reactors named Saphir and Diorit. An industrial umbrella organization, the Nationalgesellschaft zur Förderung der industriellen Atomtechnik, brought together private partners. The regional utility Energie Ouest Suisse would serve as operating partner for the prototype power station. Planners expected a stepwise path. Research reactors would inform a prototype power station, which in turn would lead to future commercial plants labeled Made in Switzerland. Technical documents show Swiss participation in European heavy water and gas-cooled designs developed in France, the United Kingdom, and Sweden. The decision crystallized around a heavy water, moderated, carbon dioxide-cooled pressure tube reactor as the heart of what would be called the Lucens project. Historian Tobias Wilde later described Lucens as the culmination of a dream of an own reactor, conceived as both an engineering experiment and a national symbol. Policy choices for autonomy and indigenous technology directly shaped the technical concept. Small, experimental, and underground features that would later define how the accident unfolded and how difficult the cleanup became. By 1962, Lucens was authorized as a pilot plant with modest output, roughly 30 megawatts thermal, 6 megawatts electric. Documents projected a demonstration period of several years, after which experience would guide commercial development. Yet this modest prototype would generate one of the country's costliest and most technically complex decommissioning projects. The contrast between ambition and outcome was already written into the design. From 1962 to 1966, construction crews excavated 3 caverns into the Molasse rock near the village of Lucens in Canton Vaud. One cavern held the reactor, a second housed the turbine and generator, a third contained auxiliary systems. Tunnels connected them to modest surface buildings and a ventilation stack. Design documents presented the underground siting as a safety feature. The rock mass would provide shielding, impact protection, and a quasi-natural containment. The later accident would confirm this function for off-site protection, but at the cost of intense contamination and confined working conditions inside. The Lucens reactor was designed for approximately 28 to 30 megawatts thermal output, generating 6 megawatts electric. Heavy water served as moderator, carbon dioxide served as coolant. Fuel consisted of uranium, enriched to roughly 0.96%, alloyed and clad in magnesium, a Magnox-type design arranged in vertical pressure tubes passing through the moderator tank. Carbon dioxide entered the channels at roughly 6.3 megapascals and 223 degrees Celsius. It exited at approximately 5.8 megapascals and 378 degrees Celsius, then transferred heat to a steam generator. Protection systems included neutron flux scram circuits, fission product monitors in the coolant stream, and weakened burst sections in pressure tubes designed to localize a rupture. The Swiss Federal Nuclear Safety Inspectorate, known by its later acronym ENSI, would describe Lucens as the first purely Swiss nuclear power plant, designed explicitly to demonstrate national capability. The rock cavern was presented as an intended functional barrier, supported by engineered ventilation and filtration, leading to the upper vent stack. The choice to use carbon dioxide and magnesium-clad fuel in pressure tubes, inside rock, established a specific vulnerability. Any water ingress or corrosion products in the channels might not be easily detectable, yet could strongly affect local cooling. Engineering memos called the cavern concept, proven in later assessments. Those same documents also listed extensive modifications to drainage and rock sealing before first criticality, hinting that the natural containment was less simple than it appeared. A damaged fuel element from the Diorit research reactor at Wurenlingen was photographed after a 1966 incident involving Lucens-type fuel. Test documentation reported partial fuel melting in magnesium-clad elements. The Diorit results suggested that Magnox-type cladding was vulnerable under off-normal conditions. Yet the Lucens fuel concept proceeded essentially unchanged, with regulatory approval into power reactor duty. Construction milestones followed in sequence. On the 29th of December, 1966, Lucens achieved first criticality. On the 29th of January, 1968, the plant delivered its first electricity to the grid. On the 10th of May, 1968, the plant was handed over to Energie Ouest Suisse after a 10-day acceptance test at or above 21 megawatts thermal. Construction reports noted water ingress into the caverns, repeated drainage improvements, and adjustments to sealing, early evidence that the underground setting presented civil engineering challenges. The Federal Safety Authority, predecessor of ENSI, supervised test operation and recorded repeated issues with carbon dioxide blower seals and coolant system reliability. ENSI's retrospective analysis noted that serious problems with circulation blowers and water leakage were documented during the test phase. Known coolant system weaknesses and early fuel behavior warnings formed the background against which a 1968 revision was planned. These issues were treated as engineering problems to be solved within the project, not as reasons to reconsider the core concept. By mid-1968, Lucens was operating at rated power and fulfilling its demonstration role. Scheduled revision work that autumn, intended partly to fix blower seals, would introduce the water that later drove the accident sequence. Maintenance logs from the period show a pattern: identified problems, corrective actions, resumed operation. Each cycle built confidence that technical issues were being managed. What the logs did not show was the cumulative effect of small amounts of water entering a system designed to remain dry. On the 24th of October, 1968, Lucens entered a scheduled revision and modification period. Logs listed tasks, fuel inspections, instrumentation checks, and crucially, renovation of circulation blower shaft seals and associated seal water systems. Maintenance was expected to improve reliability and reduce nuisance leaks. Later investigations by the Untersuchungskommission Lucens, abbreviated UKL, concluded that significant water ingress into the primary carbon dioxide circuit actually occurred during this period. Seal water systems on high-pressure carbon dioxide blowers used water barriers to prevent gas leakage. Malfunctions or tests could introduce water into the gas stream. Once in hot channels, water could condense and promote corrosion of magnesium cladding and steel components. Corrosion products would dislodge and be transported as particulate in the carbon dioxide loop. ENSI's detailed accident analysis noted that the UKL traced the water to activities during this revision interval. Over weeks of downtime, water pockets and corrosion in selected fuel channels were left largely undetected. When the reactor restarted, these hidden changes would manifest as localized blockage and overheating, not as clear system-level alarms. Blower maintenance involved disassembly, seal inspection, and testing. Procedures called for verifying seal integrity before returning systems to service. What procedures did not account for was the possibility that small amounts of seal water, introduced during testing or through degraded seals, could accumulate in the carbon dioxide circuit over time. The gas stream would carry moisture to cooler regions, where it would condense. In vertical fuel channels, condensate could pool in lower sections. In the presence of hot magnesium and uranium, chemical reactions would begin. By mid-January 1969, Lucens was cleared to restart. The revision that should have improved safety had instead left behind invisible corrosion deposits in fuel channel 59. Workers completed final checks. Instruments were calibrated, the control room prepared for startup. Nothing in the documentation suggested that conditions inside one channel had fundamentally changed. Startup procedures for the first power operation after revision called for a slow approach to full power. According to later reconstructions, the reactor reached criticality in the early hours of the 21st of January, 1969. Power was gradually raised toward a planned daytime grid connection. Operators expected a routine power escalation within licensed limits, guided by neutron flux, temperature, and carbon dioxide flow indications. The accident sequence would unfold without any advanced indication that clearly pointed to a blocked channel or imminent tube failure. Available instrumentation included global neutron flux channels, primary circuit pressures and temperatures, carbon dioxide blower currents and flows, and fission product monitors in the gas stream. No individual fuel channel flow or temperature measurement existed. Local anomalies would manifest only indirectly through system-wide readings. A paper published in 1980 by Andreas Fritzsche in the journal Nuclear Safety emphasized the extremely complex chain of events and noted that no advanced indications were observed at the time that operators could clearly interpret as a developing major fault. System-wide measurements stayed within permitted ranges, giving the shift supervisor no documentary reason to halt the startup. Control room logs showed the time 0423 when the reactor was recorded as critical. Neutron flux increased smoothly. Carbon dioxide circulation began. Blower currents matched expected values. Primary circuit pressure stabilized. Temperature readings climbed according to heat balance predictions. Power escalation proceeded in steps, with holds at designated levels to verify system response. As power rose, channel 59, already narrowed by corrosion products, operated with reduced cooling margin. The blockage was partial, not complete. Flow continued, but at a rate insufficient to match heat generation at higher power levels. Cladding temperature in that channel began to exceed design limits. The fuel matrix heated beyond normal operating conditions, yet global instrumentation showed nothing unusual. By late afternoon, Lucens was at roughly a quarter of its thermal rating and approaching planned objectives precisely when fission product monitors and protection logic began to respond to conditions in one unseen channel. Analysis later showed that fuel element and channel 59 was the locus of the initiating failure. Corrosion products had constricted the carbon dioxide flow area, degrading heat removal as power increased. Design calculations assumed clean gas paths and uniform cooling. Any blocked channel event was expected to be rare and, if it occurred, to be detectable via temperature excursions before serious fuel damage. In reality, the first unambiguous indicator was rising fission product activity. The thermal hydraulic evolution followed a documented sequence. Reduced carbon dioxide flow led to rising cladding and fuel temperature. Magnesium alloy cladding weakened and began to react in a carbon dioxide environment in the presence of residual water, forming hydrogen and oxide. Fuel matrix damage led to release of fission products into the channel and primary gas. Fission product monitors detected increased activity. Protection logic ordered a rapid shutdown, known as a scram. The reactor became subcritical. The chain reaction stopped, but the mechanical state of the overheated pressure tube continued to deteriorate. NC's analysis and subsequent literature agreed that the pressure tube failure occurred shortly after scram, not before. This distinction was critical. The protection system, tuned to radiological and neutronic conditions, did its job. The deeper issue was localized thermal mechanical overload in one channel, driven by corrosion and blocked flow the system was never instrumented to see. Within seconds of the scram, the weakened pressure tube in channel 59 failed. What had been a fuel element incident transformed into a loss of coolant and contamination event in a closed cavern. The transition was rapid. Operators watching control room instruments saw pressure transients, system alarms, and a cascade of indications that the reactor had suffered a major structural failure. A protection system can stop a nuclear reaction. It cannot reverse thermal damage already in motion. It cannot repair a corroded tube on the verge of rupture. The scram worked as designed. the channel failed anyway. This paradox between neutronic control and mechanical integrity defined the Lucens accident. Pressure and acoustic disturbances in the primary carbon dioxide system, recorded in logs and reconstructions, corresponded to rupture of the pressure tube surrounding Channel 59 and damage to adjacent structures. Safety analyses had examined blocked channel scenarios and specified weakened tube sections and burst discs to confine damage. These features functioned as intended. Yet, because the reactor was in a rock cavern, the release was concentrated in the underground volume rather than diluted in open air. The rupture sequence began with expulsion of carbon dioxide, steam, fuel fragments, and structural debris. Loss of approximately 1,100 kilograms of heavy water from the moderator system into the cavern followed. The source term was dominated initially by short-lived fission products, such as rubidium-88 and krypton-88 carried in the gas phase. Dose rate surveys soon showed values around 1 sievert per hour, in parts of the cavern 100 rem per hour, orders of magnitude above normal occupational fields. International accident reviews and NC summaries both described the Lucens event as a partial core melt with massive contamination of the cavern, but no off-site deterministic health effects. The tube rupture converted a local overheating problem into a whole cavern contamination and access crisis. The rock that was supposed to keep the public safe now trapped high activity in a confined space, complicating every subsequent response. Control room staff verified from Neutron and system indications that the reactor was shut down and decay heat was being removed. But cavern access now implied entering an area where dose rates could reach lethal levels within an hour. Hot gas and aerosols dispersed in the confined volume, contamination deposited on rock walls and equipment. High dose rate zones formed near the damaged core. The cavern's ventilation system, designed to filter and control releases, faced a challenge beyond its design basis. Engineers outside the cavern assessed the situation through instrument readings and calculations. Entry would require extensive protective measures and strict time limits. The immediate question was not how to repair the reactor, but how to stabilize it and protect personnel. Emergency plans were activated on the 21st of January. Non-essential personnel withdrew. Access to the caverns was restricted. Ventilation routes were reconfigured to minimize uncontrolled releases while protecting equipment and allowing decay heat removal. The plan anticipated incidents with limited releases and rapid access for manual intervention. Instead, initial dose conditions inside the cavern were too high for safe entry without delay and substantial protective measures. Radiological protection actions began immediately. Installation of temporary shielding and monitoring points followed. Use of air-supplied protective suits was mandated, with strict time limits per entry. Off-site dose rate mapping and sampling of air, soil, and water in nearby communities was initiated. Off-site monitoring results, summarized in UKL and NC publications, showed noble gas releases leading to public effective doses around 0.001 millisieverts. Tritium, from heavy water, contributed up to approximately 0.05 millisieverts to the most exposed individuals. Both values were well below contemporary limits and much lower than annual natural background of roughly 1 millisievert per year locally. The UKL and later NC reports stated that neither workers nor the public received doses exceeding legal limits and that no deterministic health effects occurred. Emergency procedures, coupled with the cavern barrier, successfully protected the surrounding population but created a new operational reality. The main challenge was no longer evacuation, but long-term recovery of a heavily contaminated, hard-to-access underground plant. When the accident was later graded as INES Level 4 accident with local consequences, the label captured a paradox. For the public, Lucens barely registered in dose statistics. Noble gas doses were in the microsievert range. Tritium doses were a fraction of natural background. No evacuations were ordered. No emergency food restrictions were imposed. For engineers and regulators, however, Lucens became a case study in how an experimental design could fail catastrophically in terms of plant damage while succeeding in its fundamental safety function of protecting the surrounding population. The Untersuchungskommission Lucens was convened under federal authority in 1969 to provide a comprehensive technical and radiological assessment. Tables filled with damaged components, metallographic samples, and logs from the accident day. Early press summaries described a meltdown in an underground reactor. The Commission's mandate was narrower and more technical: establish the precise chain of events, quantify doses, and assess design adequacy. UKL and related technical papers reconstructed the sequence. Water ingress via blower seal systems during the 1968 revision led to corrosion of magnesium cladding and structural materials. Accumulation of corrosion products caused partial blockage in Channel 59. Overheating, fuel and cladding damage, tube rupture, and heavy water ejection followed. The Commission confirmed that failure modes similar to this scenario had been contemplated in pre-accident safety documentation, but the likelihood of significant blockage and its detectability had been underestimated. Fritscher's 1980 article noted that the chain of events was extremely complex and that the disquieting lack of clear early indicators was a key focus of analysis. The Commission's work extended through the 1970s, with final reports issued in 1979. Investigators examined every aspect: fuel design, coolant chemistry, instrumentation capability, maintenance procedures, and operator training. UKL's findings shifted attention from a single error to a network of factors: water management, instrumentation limits, maintenance practices, and the choice of fuel and coolant all contributed. Each step made a known failure mode harder to see in time. The Commission also analysed dose pathways in detail. Off-site impact was confirmed as minimal. Worker doses during the accident and immediate response remained within regulatory limits, though some individuals approached annual limits in the days following the event. While UKL confirmed that off-site impact was minimal, its report also concluded that Lucens was not realistically repairable. The economic and technical case for restarting the reactor was gone. Damaged core components, contaminated systems, and the programmatic shift away from heavy water technology all pointed toward permanent shutdown and decommissioning. Photographs from Swiss archives showed workers in full protective suits standing near the opened reactor vessel, surrounded by temporary shielding and decontamination equipment. Lucens was never designed as a decommissioning training ground. The assumption was safe operation followed by conventional shutdown. Instead, it became a live experiment in post-accident cleanup in a confined underground space. The main phases began with allowing decay of short-lived isotopes to reduce dose rates. Construction of airlocks, decontamination sluices, and controlled pathways within the caverns followed. Mechanical decontamination using high-pressure water, chemical agents, and surface removal on rock walls and equipment began in the early 1970s. Segmentation of damaged core and circuit components, and packaging as waste, continued through the decade. By the early 1970s, sources reported around 250 drums of radioactive waste produced from decontamination and dismantling. Decommissioning summaries indicated collective doses on the order of 1 man-sievert, approximately 100 rems spread over the workforce. Individual annual doses were kept below then-permitted limits through time management and shielding. IAEA documentation on on-site disposal cited Lucens as an example of a plant where decontamination and partial dismantling preceded long-term immobilization of residual activity in concrete-filled caverns. The underground geometry required tailored tools, restricted work shifts, and creative shielding solutions. Cleanup was achievable, but at far greater complexity and cost than for an equivalent surface installation. Work proceeded in phases dictated by dose rates. Initial entries were limited to 15 to 20 minutes. As contamination was reduced and shielding improved, work periods extended. High-activity components were removed first. Lower-level surface contamination was addressed through washing and chemical treatment. Rock surfaces presented unique challenges. Porous molasse absorbed contamination, requiring removal of surface layers in some areas. By the mid-1970s, major decontamination work was complete. The reactor cavern remained too activated for unrestricted reuse, forcing a strategic choice about final disposal. The site was not abandoned. It was transformed from an operating nuclear facility into a controlled waste repository, with components too contaminated to remove left in place and sealed in concrete. Technical drawings from the 1980s showed concrete backfilling of the reactor and fuel storage caverns, sealing remaining contaminated structures and rock surfaces under a permanent barrier. The plant was expected to operate to the end of 1969 for experience gathering and then be shut down on economic grounds. Instead, Lucens was formally decommissioned following an accident, and its caverns were partially filled as a disposal option. IAEA case studies described Lucens as a textbook example of on-site disposal. High-activity components remained in situ, immobilized in concrete and rock. Lower-level wastes were packaged and later moved to central interim storage. Swiss nuclear policy histories noted that by the late 1960s, independent of the accident, international trends favored light-water reactors, abundant enriched uranium supply, and large unit sizes. The Lucens heavy water line was already losing strategic relevance. The accident effectively ended it. Sources cited accident and decommissioning costs around tens of millions of US dollars in contemporary value, plus the write-off of the experimental reactor and associated research and development investments. The national program, built around an indigenous heavy water concept, was overtaken by technological and economic realities and by the practical experience of an accident that made continuation politically and financially unattractive. Switzerland's subsequent nuclear program focused entirely on light water reactors, pressurized water reactors of proven international designs, with standardized fuel cycles and established safety records. Besnau, Mühleberg, Görsgen, and Liebstadt, the country's commercial nuclear plants, bore no technical resemblance to Lucens. The heavy water path was closed. Swissinfo's 2003 retrospective quoted officials calling Lucens' final waste removal the end of a historic chapter for Swiss nuclear development. By 1988, Lucens was formally removed from the list of operating nuclear facilities. The site was no longer a power station, but it was not yet just another industrial building. Residual activity in the rock remained under supervision. Monitoring continued. Drainage water required periodic analysis. The caverns were sealed but not forgotten. News photos from 2003 showed shielded transport casks leaving Lucens, heading roughly 160 kilometers to the National Interim Storage Site at Wurenlingen with about 300 tons of material, the last movable radioactive inventory from the plant. Where once electrical output figures were reported, official statements now focused on tonnage of waste, truck convoys, and regulatory clearance for a site that no longer produced power. Key steps in the final phase included partial filling of remaining voids between 1992 and 1995, final decontamination, and declaration of entnuclearization status, removal of remaining activated components and wastes in several heavy transports to Wurenlingen, followed in 2003. Surface buildings and some cavern space were repurposed as cantonal, cultural, and archaeological storage, later also hosting film archives uses compatible with low residual radiation levels. Swissinfo's report on the last waste shipments emphasized that Lucens was Switzerland's first nuclear plant decommissioned, symbolically closing an early experimental phase. Decades of monitoring, decontamination, and phased waste removal turned Lucens from an active hazard into a controlled, low-impact legacy site with alternative uses. The transformation was complete. The reactor cavern, once the heart of a national technological ambition, became a repository for museum artifacts and historical documents. Film reels and archaeological finds occupied spaces where control rods and fuel assemblies once stood. Visitors to the surface facilities saw no hint of the nuclear history beneath their feet. Only drainage monitoring points and occasional radiation surveys remained as physical reminders that a reactor once operated beneath the hill. With the final waste containers gone, Lucens exited the nuclear industry except as a case study. Regulatory oversight shifted from operational safety to environmental monitoring. The site posed no immediate hazard, but prudence dictated continued attention. Tritium in drainage water, though far below health-based limits, provided a measurable signal of residual activity sealed in concrete and rock. Recent monitoring reports from the Federal Office of Public Health, known as BAG, showed tritium in drainage water at typical levels around 15 becquerels per litre, with occasional peaks up to about 230 becquerels per litre, still far below the World Health Organization drinking water guideline of 10,000 becquerels per litre for tritium. Where early headlines spoke of a meltdown in a mountain, the long-term picture was one of modest residual releases, tightly controlled and well below health-based limits, yet requiring continued surveillance. Documented lessons highlighted by NC and historians included several key points. Underground siting could be effective containment, but complicated access, decontamination, and instrumentation. Water management in gas-cooled, magnesium-clad systems was critical. Identified accident scenarios must be integrated into maintenance and monitoring practices, not just design documents. Decommissioning and on-site disposal strategies must exist even for prototypes. Lucens now appeared in international reviews as an INES 4 event. Severe local damage and high on-site dose rates, negligible off-site health effects, and substantial programmatic consequences. INES's retrospective noted that Lucens contributed to making safety the top priority in Swiss nuclear policy as the country shifted to standardized light water reactors and strengthened central oversight. A small experimental plant, intended as a stepping stone toward a national reactor line, ended up shaping regulatory expectations on design diversity, prototype operation, and decommissioning precisely because its failure was serious, yet contained. The cavern concept worked. Public doses remained far below regulatory limits and within natural background variability. But the cost in terms of facility loss, decommissioning complexity, and programmatic redirection was profound. Today, Lucens is absent from power production statistics, but present in safety case studies and decommissioning manuals. It serves as a documented reminder that even low-power prototypes can generate decades of technical, regulatory, and financial work when hidden failure modes meet novel design choices. The rock that promised containment delivered on that promise, but also preserved evidence of failure that engineers and regulators continue to study more than 5 decades later.